today's session. Okay, hello everyone. I hope you had a great break and started a very good week so far and uh, enjoyed the time off. So far, through the semester, we talked about the inverters and how we could control the inverters, the THD, the power quality, the different type of inverters, how we could categorize them, how we could control them, what are the differences between the controlling system of the different categories of the inverters. We talked about the grid following, we talked about the grid forming. But so far, all our discussion was based on the component, the inverters alone. Okay. So we didn't talk about the system perspective of how IBRs or like inverter-based resources would work within a system. From now on, our discussion is going to be around system analysis. Like we are going to learn how we could analyze the system integrated with IBRs and what would be the effect of that inverter-based resources compared to the conventional rotary machine resources that we already have in our system. Now, today we are going to start with power flow analysis, which is the very basic analysis of the system when we talk about the power system. Okay? Work with me, please. Okay. Anyone knows anything like, did any one of you already heard or like thought about the power flow analysis for the power system? I assume you did, yeah. And so how about you guys? No? Okay. Okay, so let's start from the base of the power system analysis. So what we talk about the power flow, basically we want to analyze the flow of energy between different points in our grid. Okay, so that being said, one of the most important aspects of that analysis would be the grid itself, right? The network of all those nodes, or what we call it in power buses, that connected to each other and create the system that we want to like analyze the power flow within that system. Okay. Now, if the important part is one of the important part is grid itself, the topology and like the system itself, how we can model the system, because what we have in real life is a topological kind of like distribution of a bunch of loads and generators connected with transmission lines or distribution lines. But how we could model them mathematically, so we could use numerical methods or like any other analytical methods to analyze the behavior of that system in different situation, in different condition. Okay, now the concept of the admittance matrix, as you could see in the display in the slides, is actually the foundation of the network analysis. Admittance matrix is the mathematical representation that we use to represent that topological graph, the topological grid that we have in real life in the field. Okay, but what is admittance matrix? Admittance matrix, okay, relate directly to how much current injected from each node or between each two nodes. Okay, when I say nodes, sometimes I'm gonna call it bus because it's gonna be the same. The term bus is the same as the nodes in system analysis in power system. Okay, so now there are several key properties into the admittance matrix. We are going to see how we could shape the admittance matrix from the grid in the next slides, but let's talk about the properties of that and get over with that, then we go to the how we could develop the admittance matrix from an actual grid. First property is that the admittance matrix is symmetric. Okay, as we said, admittance matrix models. Come on. Admittance matrix models the connections between the nodes. Correct? So it makes sense that when we have a mathematical number or like a number, a scalar, or a complex number, whatever, okay, that represent how node 1 or bus 1 is connected to bus 2, okay, and we would have a matrix that number, this is y1, 2, shows the quantity, a quantity representation of how bus 1 and 2 are connected to each other. Makes sense that when we have y21, which is how bus 2 and 1 is connected, they should be the same. Correct? So basically, this makes sense that the admittance matrix has a symmetric kind of like behavior, like symmetric properties within it. Now, yeah. So another property is that all the diagonal elements, meaning like for example here, y11, y22, okay, are gonna be the sum of all the branches, all the admittances connected to that specific bus number. This is also comes with a definition. You say if admittance 2, 1 is the admittance connected between bus 2 and 1. So admittance 1, 1 is all the admittances that are connected to 1. Make sense?
Or if it's 3, be 1, 2.
No, is if it's like 1, 1, 2, 2 are all the admittances that connected to 2, to bus 2. And y 3, 3 is all the admittances to the connected to the bus 3. It doesn't necessarily means that these two buses are connected to each other, because this is could be bus 1, bus 2, and bus 3. Admittances that connected to the bus 3 are not the same as admittances connected to bus 1. So individually, y11 is the sum of all the admittances connected to that bus. So maybe there is another line here that connects 1 to 4. Now, 1, 1 is the summation of this admittance and this admittance. Is that clear?
No. But if 3 is connected to 1 in that configuration, what
Is not. 3 is connected to 2, 2 connected to 1.
Oh, it's
Yeah. Are we-
Something's different.
Yeah. Are we good? Is that clear now? Yeah. Okay. So this is also what we talked about, the diagonal element. Now, off diagonal elements, the one here and here, okay, they're all quantitatively are the negative of the admittance connecting those buses. So if in real life you have an admittance of like 10 Siemens, okay, connecting bus 1 and 4, the y14 is going to be minus 10. Are we good? So the negative value of the admittance connected between the two buses are the off-diagonal elements. Now, let's try to see an example of how we could develop a admittance matrix. Is there any question so far? Go ahead.
Why did they say?
you wanted to represent actually like this is the reason within that development you will find the reason you wanted to like analyze the behavior of power grid. Okay, one of the behaviors of the power grid is power flow analysis. How energy would flow. What is the energy flow? Is the current. Correct? So what eventually you are gonna analyze is how much current is flowing through each branch in your power grid. Okay? How you can measure the current of each branch? You need to measure the voltages, okay, and use either impedance or admittance, which are basically the same, okay, and calculate that current. Make sense? So admittance comes from that. Now, there is a deeper conception of the admittance and impedance matrix because system in general system analysis perspective, okay, not power system perspective. Actually, it is one of the power system perspective, but it's not a standard kind of curriculum, okay? But generally, in system analysis, admittance matrix is called topological graph, okay? Remember that, okay? I want you to like search on that. Admittance matrix is topological graph. Impedance matrix is complete graph. Very different component. They represent the same system, very different concept. Okay, and it really, if you search on that and you understand the difference between the topological graph and a complete graph, you would get a very good intuition about the system analysis and how systems work. Okay, so now let's try to develop an admittance matrix for this system. We have a power grid shown in a circuit with 4 buses. And these 4 buses or 4 nodes connected with some transmission line or like any kind of like distribution line to each other. Each line would have an impedance or admittance, okay, from electrical circuit analysis perspective. Correct? Because there is a resistance, inductance, and capacitance. So there is going to be an impedance or admittance. Okay? Now, in order to calculate or develop the admittance matrix, we simply run KCL through our system. Now, let's go for the I1. What is I1? If you do the KCL in bus 1, which is the node 1, you know KCL means the summation of all the current should be 0 regarding the direction. Okay, so injecting current is equal to the consuming current. Current in equal to current out. Okay, so now here we have this 1 to 3 current plus 1 to 2 current, and it should be equal to I1. Correct? This is a KCL. Now, what is that current value? This current value, if you do that, is basically the difference of the voltage 3 and 1 multiply by the admittance between them. This is Ohm law. Are we good? So V3 minus V1 or V1 minus V3 times admittance. Okay, now, same goes here. We do the KCL for the bus 2, find out the current. KCL for bus 3 and bus 4. Now we reorganize all those voltage times impedance, admittances, so we could factorize each admittance from those values. Make sense? Is that clear? So if you do that, you would see that V1 is multiply in order to calculate the I1. If you want to calculate the I1, for all the equations, V1 is multiplied by these admittances. V2 is multiplied by this one, V3 this one, and V4 this one. And you have 4 equations for all the 4 currents. Make sense? Is that clear how we reach that? Is a KCL and Ohm law. And then we reorganized so we could factorize the voltages from all the parameters, from all the terms in the KCL equation. Are we good? So now, look at this one. We have 4 variables, 4 unknown. Let's represent it with a matrix form. If we want to represent the matrix form, we could represent the currents in a matrix, and it's going to be equal to those coefficients, let's call it coefficients, times our variables. Now, look at the matrix alone. What is I1? I1 is the row 1 times the variable when you do the multiplication in matrix, correct? So it's going to be the same as this equation. Same goes on and on. So if you rewrite the KCL in a matrix form, the coefficient matrix that you have in your equation is going to be your admittance matrix. Go ahead. What do you mean?
Well, it has 34, 23.
No.
4.
One. No. 4, 1. Why 4, 1? Admittance between this Y 41 means the admittance between bus 1 and 4, or 4 and 1. It's not 41, it's 4, 1. It is, okay, so, no, okay, what is the value of admittance that connect directly 4 to 1? Do we have admittance? No, directly. Don't do, yeah, directly connect 4 to 1. What is the admittance? Directly, do not do the analysis. Is there any direct branch that connects bus 4 to bus 1? So we don't have admittance. So this is 0. Are we? So
Oh, okay, so it's not saying it's
yeah,
saying
this is general equation. Okay, so now if we don't have an admittance between 4 and 1, that means this one is 0. Same as we saying that the 4 and 1 are open circuit with each other. So the impedance is infinity, right? So the admittance is 0. Make sense? Now, for 1, 3 has an admittance. 1 and 2 has an admittance. But 1 and 4, we don't have a straight connection, a direct connection. So it's 0. That's the meaning of topological graph. It's topological graph. It's actually what's out there. Now, if you wanted to like represent this is in parentheses. I don't want you to like confuse you. This is like, for example, the admittance matrix for this graph, for this grid. Okay, so if instead of admittance matrix, you want to represent it by impedance matrix, try to do that for one example. All the zeros will get a number because admittance, impedance is admittance reverse. So even if you have a zeros in your admittance matrix, when you calculate the reverse of that impedance, that matrix, all those zeros is gonna go away. So this is the difference. This is the concept. If you I want you to think about that. Why? Where those zero goes? Because we don't have, like for example, we don't have a straight connection between 1 and 4 in admittance matrix in topological graph. So it's 0. But same system, if instead of admittance matrix, I show it by impedance matrix, now there is a quantity that shows the connection between 1 and 4. And it's not 0 and it's not infinity. Okay? Where that number came from. This is the difference between the topological graph and complete graph. I want you to like search on that and try to have an intuition about that. Are we good so far? So this is how we step by step could create a admittance matrix. Now, this is the theoretical way. As we said, admittance matrix is topological graph. You can just create a matrix. Okay, 1, 2 is going to be the same as admittance between 1 and 2. Okay, you directly could enter the values. Are we good? Now that we have our system with a quantitative kind of like representation, now we could talk about, okay, let's analyze how the energy would flow, how the power would flow through our system. Okay? For that, one thing we need to know is that when we talk about the power flow, as we mentioned that, we talk about the currents flowing through branches. By the Ohm law, this is the combination of the Ohm law and KCL. By the Ohm law, we know that the summation of all the current for bus 1 or bus K, okay, current for bus K is the summation of all the current that goes in and goes out of bus K. Are we good? This is a KCL. Now, what are those currents? From Ohm's law, we know that they are admittance and the voltage difference. Correct? Now, we wanted to like talk about the power flow. Are you familiar with the complex power? Anyone here is that yet not familiar with the complex power? I'm gonna give you a very brief kind of like explanation. In DC system, you already know that the power is VI. Correct? When we talk about the AC system, these are not simple scalar. They are complex number because they are vectors. So now these two, if you calculate the instantaneous power, now these two would have both real values and imaginary values because we're talking about two vectors. Okay? So we show the power in AC system or power system with S, we call it complex power or apparent power, which is a complex number equal to the active power plus reactive power. Is that clear? Now, the formula of S, when you want to calculate the S from voltage and current, is voltage times I conjugate. So let's do that. For bus K, the power would be the voltage of bus K times the current of bus K conjugate. But we know the current of bus K conjugate is that summation. We already know that from KCL and Ohm law. So let's do that. Conjugate of this means conjugate of the admittance times conjugate of the voltage. Let's expand that formula. We keep the voltage outside here as is. The voltage, this is a vector, conjugate, is the amplitude of voltage times minus theta. Are we good? So instead of V e to the power of minus j theta, we have e to the power of j theta. So this is the conjugate of the voltage. Now, the admittance in you probably remember that from circuit analysis, the admittance is B plus JG. Okay? The conjugate of that become G minus JB. So sorry, GB. So the conjugate become G minus JB. Are we good? We just change the plus side in a complex number to the minus side. Is that clear? Any question about that? Now, this e to the power of j theta, this is a, if you expand it, it becomes cosine plus j sine. It's a trigonometric kind of like expansion of the exponential function. Okay, you already know that. Let's expand that. And now, if you do the multiplications, all the multiplications, you would see the real part of this S, which we call it active power, is going to be the summation of V I V K G times cosine of theta plus B times sine of theta. This is just the multiplication of these two. Okay? And the Q become VI G times sine of theta and B times cosine of theta. So now we have our active power and reactive power based on our voltages, thetas, and admittances. Are we clear? So we have power flow equations. How power flow from each bus to the other one. Any question about that? Now, depend on the information that you have for each of the buses. You normally, so if you look at this formula, P, Q, these are known voltage and theta. So 1, 2, 3, 4. We have 4 unknown or variable. But normally, when you want to like analyze the system, you already know 2 of them. So either you know P and Q, and you want to find the other 2 voltages and thetas, or you know, for example, P and voltages, and you want to find out what is the Q and thetas. So you know 2 of them, you want to find the other 2 from those 4 variables. Based on that known and unknown variables, you rewrite that power flow equation that we had and try to numerically solve to find the unknown until we get to an acceptable kind of like error margin. Is that clear? This is how we run the power flow problem. Now, one of the methods, let me see if I have that here. No. Okay, before I move on, I mentioned, so this is the P, this is the formula for P, this is the formula for Q, okay? Before midterm, I mentioned that when we want to control the inverters, controlling the theta, okay? Controlling the theta would makes the active power control, and controlling the voltage would make the reactive power control. You remember that? Now, when you look at this P and Q, you see P and Q relate to both voltage and theta. Both of them are function of both voltage and theta. So how come you can deal with that paradox? Because we already said that P changes with theta, Q changes with voltage. So here in Q, we shouldn't have this part. And in P, we shouldn't have this part as a variable. Make sense? Now, how is that going to happen? In real power grid, because transmission lines are mostly inductive and a little bit capacitive, and the resistance versus the inductance are negligible, basically, are so low that we could neglect that. Okay, if you run the analysis and if you find that, okay, if R, the resistance of those lines are basically going to 0, what happens to the admittance of that specific line is that G goes to 0. You want? Go ahead.
I just. You didn't switch, G and B also, did you? You just put a minus in?
Yeah.
Okay.
So, oh, no. Yeah. So G goes to 0. If R goes to 0, you can do the calculation. Okay, find out admittance from impedance. If you do that, it's basically it's 1 over R plus, R plus JX. Do this calculation, it's going to be multiplied by R minus JX, correct? If you do those multiplication, you would find that the G is a function of R in the denominator, and B is a function of X in the denominator. And denominator is a constant number. Correct? So if R goes to 0, that means G goes to 0. Correct? Are we good? So if G goes to 0, this term and this term are eliminated. So what we have is amplitude of the voltage, B sine of theta. Now, one of the constraints that we said in control system was we don't want a huge variation in voltage amplitude and in frequency. We wanted to like keep them solid. That was why we introduced grid forming. You remember that? So if grid should work on a stable voltage, what that means? That means the voltage between J and K should not vary too much. So these two should basically be very close to each other. In a per unit system, you could consider both of them as 1. Correct? Are we good for that? So now these two become 1. Or constant number. You don't need to put it in per unit. And if we have a stable system, that means our theta is also not varying too much. So theta between J and K is also a small number. What is the approximation of the sine of theta is small? Anyone knows that? No, sine of theta if theta is small. It's not 0, it's a small. Okay, so sine of theta when theta is small is equal to theta itself. Or we could approximate sine of theta with theta for the small, very small thetas. How about cosine? Cosine of theta for very small thetas are approximated as 1. Are we good? So this become theta, this become 1. What happened to our P and Q? Our P become voltage I, voltage J, theta I, J I J. Correct? And this B here. And our Q become voltage, voltage B, done. These are solid, these are constant number. If these two are very close to each other, that means what actually changed P is the variation is theta. And here, the only variable that we have is these two V. So Q is a function of variation in voltage. Does that make sense? So this is, I want to like you to understand where that idea of controlling P by theta and Q by V comes from. This is from these formulas. We simplify that by approximation of the real system, and we reach to that idea. Are we good? Now, in the problem solving, we said because we have a complex grid, so it means we have a huge matrix normally. Okay, we can analytically solve that. It's not that easy to solve that analytically. So it's best to use numerical method to solve or analyze the power flow. One of the basic numerical methods for solving such a problem is Newton-Raphson method. Okay, so basically we use the Newton-Raphson method to analyze that function, that matrix function, I equal to admittance V. Or in general, that PQ equal to those admittances and our V and thetas. Okay? How it works, Newton-Raphson? Newton-Raphson, you guess a number for initial value, okay? You calculate the P's and Q's, and you use the power balance rule to find how much you are off the real numbers. What is the power balance rule? Power balance rules says the flow of power between two buses, or like the flow of power going outside of one bus or getting into one bus. So the transferring power for each bus should be equal to the generation of that power on that bus and the demand that bus sees. Make sense? So the summation of all these should be 0. Now, yeah, go on.
When you're talking about demand, is this just like events where it's directly connected?
Yes, directly connected to that bus. So basically means you have a bus, there is a generator here, there is a load here, and there's a line that's going out of that bus. Simple KCL says that these current should add up to 0. This current represent generation power, this current represent demand power, and this current represent the transfer power that goes in or out of that bus based on how much demand and generations. So KCL says it should be 0. We use that power balance idea to find out if our guess is close to real value or not. Because if it's not close, this would not be 0. Are we good? Now, and then when you have it's iterative kind of like situation. You guess, you check, it's not acceptable, the error is too much, you try another guess. Now, the second guess and the third guess, we don't want to like haphazardly guess, randomly put a number in it. We wanted to like have a more efficient way to do that. That's when Newton-Raphson methods comes in. Because Newton-Raphson helps you to find a reasonable second guess based on the situation of the first guess. Now, we already talked about the power balance. So this is what we have to use to analyze if our guess is right or not. So the power balance actually shows how off we are from the accurate solution. We already talked about that. Doesn't matter. Let's go to the system. In order to do that, okay, we said normally either P or Q is known and V or theta is unknown, for those variables, or P or V is known, Q and theta are unknown. Okay. Now, let me explain something. Sorry, I'm jumping a little bit back and forth. In real life, in real power analysis, we only have 3 types of buses for power analysis: PQ, PV, and a slack. PQ buses are the buses where the situation is that you know P and Q of the bus, you want to find the voltage and theta. PV buses are the situation when you know P and V, you want to find Q and theta. Slack buses, which is not a slack buses, actually slack bus, it's one bus that we consider a slack, is the reference that you choose for your system. So you choose one of the buses as a slack, it doesn't matter which one, and you consider that as the reference. So the voltage of that slack bus is always 1 per unit, and the theta is always 0. No,
PQ.
no. Sorry?
So it's PQ or B, you choose as your reference.
And no, yeah, slack buses in the system either are PV or PQ. Okay? You have a graph.
Those you choose.
Yeah. One of the buses you choose, put it aside, and you label it as a reference or a slack bus.
But it's okay, but it's still.
Yeah. Now, the slack bus we consider as a reference. So the voltage we keep it always in our theoretical analysis at 1, and the theta is always going to be 0. Now, the rest are going to be values based on the power flow, and you can analyze the system compared to that reference. Make sense? Is that clear? Go ahead.
So I'm looking at that and simulate and what per unit voltage to use. Since I don't want a deviation of less than 10%, I put 0.9. Is that, if I don't want to use that as a reference, do I not put anything in there, or would that?
When you use Simulink for buses, you have a choice to choose between PQ or PV bus or a slack bus. It gives you the choice. Okay. If you use PQ, that means you know already what are the P and Qs are, and you wanted to find out the voltages and thetas. Okay, for each bus, you know P and Q, you want to find out voltage and thetas. If you have a PV bus, okay, you know P and voltages, you want to find out Q and thetas.
Yeah, but it wasn't asking me that, because I already chose P.
Okay,
What I'm
so
saying, it was asking what the per unit voltage was at the, I think this was in the load, by the way, load block, it wasn't in the, on the bus, but like in the. load
Okay,
block,
yeah.
it was per unit.
you put the load as 0.9 per unit. Okay,
That's what-
that's the situation of your system. Your slack bus is always 1, but the rest you decide or the grid decide.
Making sure if
Yeah.
I have my reference bus, one for my per unit,
Mhm.
do I put that, or do I put the deviation that I want as far? as
No,
that?
1. A slack bus is always 1.
In the load, like when I'm saying, if I have a reference, if I have bus, I'm using this as my reference, so I want that per unit as 1.
Okay.
Say I'm using bus 1 as my reference. In my load, when it asks per unit at the max, do I use the reference and say
No.
1, or do I use the deviation I want
Deviation.
as far from 1? Okay.
Deviation, because that should change. The other than a slack bus, all the voltages should change. Are we good? Okay, now that being said, like for this example, what you see here, okay, we consider a PQ situation when we know all the P's and Q's, and we want to find out the voltages and thetas. Okay, so our unknown variables are the amplitude of the voltages and amplitude of thetas, and our known variables are all the P's and Q's. Are we good? So f of x is basically those power balance equations for all the buses. And x here is the unknowns, voltages and thetas. Now, if you look carefully, you see that we only have theta 2 to n and voltage 2 to n, because the first voltage, we call it a slack bus, we consider it a slack bus, that doesn't change, the first bus. So the theta 1 and V1 is always constant as theta equal to 0, V equal to 1 per unit. So V1 and theta 1, because we chose it as a slack bus, this is a known, it's not unknown. Are we good? The rest is unknown. Now, how we could figure out how we could develop an iterative kind of like numerical solution to find out the actual numbers for theta and 1. We use Newton-Raphson. How Newton-Raphson works? Look at this picture. We guess, this is our first guess, or our n guess, maybe, okay? How Newton-Raphson works is that, okay, for that guess, you calculate the F, which was our power balance equations. We want the power balance equation to become 0, correct? So for example, in that xn, this is definitely not 0, correct? This is F. It has a value, it's not 0. So we are off. We have to guess again. Newton-Raphson uses the slope or the differential of the curves of F to help you find the next guess more efficiently. How it works? You calculate the slope or the differential of F and xn. Next guess is when that F prime, that line, hits the x-axis. It's going to be next S, next X, next guess. Now, again, you calculate the F. This is still not, this is F n plus 1. This is still not 0, correct? Again, we calculate the differential. We hit this point. This is x n plus 2. See, now we are closer to 0. And again, and again, and again, you might even like go on the other side and have to come back. That's not a big deal. You do this iteration until your F value, your value of F is lower than a certain acceptable error. And then you stop. You say, okay, that last guess is accurate enough. I want to use that. Are we good? Now, matrix-wise, if you run this, okay, matrix-wise, that x n plus 1 or like v plus 1 that I showed here is going to be the previous x minus f over f prime. Is that clear for how it works? F over f prime is the slope. Use the simple like this linear function. This linear function is x. This f prime is delta f over delta x, correct? So this is f prime is equal to f n plus 1 minus f n x n plus 1 minus x n. We do the we want the f n plus 1 to be 0 because it's our error. So when you do that, x n plus 1 minus x n become f minus f n over f prime n. We move this x n here, so x n plus 1 become x n minus f over f prime. In matrix way, how you show f prime? is the inverse of the F prime is the Jacobian matrix, and 1 over F prime is the inverse of Jacobian matrix. Jacobian matrix is basically that F prime in a matrix world. Are we good? Now, how you calculate Jacobian matrix? It's simply the partial differential of the function, okay, in respect to each of the variables. So for example, in previous one, we had P2 power balance until Pn, Q2 to the Qn power balances. That was our F. Now we want to do partial differential in regard to our variables, which were the voltages and thetas. So we have all the P's differentiated over all the thetas, all the P's differentiated over all the voltages, Q's differentiated with respect to thetas, and Q's respected to the voltages. So now we have our Jacobian. Are we good? Does that make sense? Any questions so far? Our X is all the thetas and all the V's that we don't know. And our F is all the power balance equation for P and Q's. Yeah. Are we good? Now, when you calculate the Jacobian, now actually like I put how you could calculate that. This is one of the Jacobian matrices. Like for example, one of the values, one of the P's in respect to theta. You just simply calculate the differential. So these two are constant, so the differential is going to be 0. Okay? In respect to theta, these are constant. These are constant. Cosine, the differential of cosine is minus sine. The differential of sine is cosine. And you do the same for all the other functions and variables. Are we good? So then we have our Jacobian. This is one element in our Jacobian matrix. Like for example, this is this one. And you have to do the next one for the next variable and so on and so on. Are we good?
Find the eigenvalue of this. That point that's in to the.
Calling it eigenvalue is not a quite precise terminology to use. Okay, it relates to eigenvalue. It's not exactly eigenvalues, but you use that Jacobian similar to using that F prime was in the Newton-Raphson. Yeah. Yeah, exactly. So this is actually like this. I have an example. Let's go through this example and see how we could like actually run a power flow. Okay. In this example, we have two buses that connected with a certain impedance with each other. Okay. Bus 1, we call it a slack, so it's 1 per unit. Okay. And bus 2, we want to find out what's going to happen. So the unknown in our system are theta 2 and V2. And this is a PQ kind of like situation. So we know the PQ of our bus 2 conditions. Are we good? Now, what would be the admittance matrix? If you do those problems that we said how to calculate the step-by-step admittance matrix, if you do that, you would find the values for the admittance matrix. This is a very short, a small kind of like grid, so it's easy to find that. Okay, all the admittances connected to the 1 is basically, if you reverse that, impedance is minus 10J. Are we good? The admittance of this impedance is minus 10J. So all the admittances connected to the bus 1 are that minus 10J. All the admittances connected to that bus 2 is also 1J. Now, admittance between 1 and 2 should be negative. The minus sign, the negative of the admittance between 1 and 2 is minus 10J. The negative is going to be 10J. 1, 2, 2, 1. Are we good? So now we have our admittance matrix for this simple bus system. Okay? Now, we want to run an analysis to find out what is the theta 2 and 1 and V2 is. For that, we need our power balance because this is our condition. Okay? We know the numbers, we put them, and we find our values. I just simply inserted the value of the P and Q and the admittances into that system. Yeah. Are we good? Now, let's do the Newton-Raphson values. In order to do that, we have our P2 and Q2 functions. Okay? We need a Jacobian. Jacobian is P, differential of P to the theta 2, differential of P to the V2, Q to the theta 2, Q to the V2. Do the differential. You will find the Jacobian matrix for this example. Now we have our Jacobian. Let's start guessing what are the number of. We have everything that we need. For our first guess, we say, okay, let's say the theta is 0, the voltage is 1. Is a guess. There is no reason behind that. Okay? It's a guess. If the 0 and 1 are the voltage of the theta 2 and V2, then the F, that matrix that we developed for P2 and Q2, okay, the power balance, would end up being 2 and 1 instead of 0 and 0. So we are way off. Are we good? Now, let's calculate the Jacobian for that values, for the guess that we have. And based on the formula of Newton-Raphson, let's find the second guess, the reasonable second guess. Use that formula, x0 minus inverse of Jacobian, fx0, okay? And we find a reasonable second guess. We put that to the action. We find, okay, for the second guess, what would be our f? See, is much closer to 0. It's still not close enough. We calculate the Jacobian for the second guess, so we could calculate the third guess. Use the same formula. Now we have a more closer, or like more accurate guess to the actual value. Let's try this one to see how close it is to the actual value. F of 2, we are still 1% off. More than 1%. So let's not accept it. We do the same iteration and find the fourth guess. This is our fourth guess. For this guess, we calculate the F. We see, okay, now we are quite close to 0. And we say, okay, that's enough. I'm okay with that small error. Close enough, we accept that. So the voltage and theta of bus 2 are 0.8554 per unit and minus 30.52 degree. This is radian, okay? Yes. Are we good? So this is how we use a power flow, a Newton-Raphson, to calculate the power flow. Any questions so far? So what we learn here is that, okay, first of all, we learn how to quantitatively represent our topological grid using admittance matrix. We learn how to develop the admittance matrix from the actual grid that we have out there. Okay. We mentioned, okay, what is the impedance matrix and admittance matrix and what is the difference? Topological graph, complete graph. Search on that. That's a very good concept. Okay. Then we learn, okay, what is the situation? In each bus, we have P, Q, V, and theta as our variables. Every time that we want to analyze, we know two of them, we want to find the other two. So if we know P and Q, we want to find V and theta. And then we use the power balance situation, which is a very basic fundamental rule based on KCL, in order to find out that our solution is accurate or not. Because if we if our solution is not consistent with KCL, that basically means that our solution is worthless. Okay, because we are kind of contradicting with the fundamental laws. Okay, so we use that to check out our solution as a condition of our numerical method. And we start and we learn how Newton-Raphson method, which is the most simple, basic, iterative numerical solution method, how that works, and how we could use it to efficiently and fastly reach to the accurate solution. And we run an example of one simple grid to know, okay, what actually this works and how we could do such an analysis for the power flow analysis. This is the general power flow analysis, because I assume that you didn't pass any courses that teach you what is the meaning of the power flow analysis. This session, we only talked about the power flow analysis in general sense. On Thursday, we are going to talk about, okay, what is the situation when inverters kicks in? What is the difference? This is general one that we use. Okay, are we good? Any question? Go ahead.
When you say iterative. So you've got inverse, what you use for F1, do you not use the
No, see, this is the F. We have a guess. We have the first guess, x0, x0. Okay. We check with our condition, that power balance condition, to see if it's accurate or not. We calculate the F. We see it should be equal to 0, but it's equal to 2 and 1. So definitely this guess is not accurate. So let's use the Jacobian matrix, the Newton-Raphson, to find what should be our second guess. Based on the Newton-Raphson, we find the second guess. That formula, this was the curve, the slope is Jacobian, hits the x-axis. This is our second guess.
but just in this. When you find, so this 10, 0, 0, 10.
This is the Jacobian matrix for this graph, yeah.
So two different. Then they can happen with it.
J, Jacobian, is round. No, two different. J is the partial differential of all the f's, regard all the variables. So
But I think, I'm trying to see do you
So
use-
this is xn. No, this is the formula is x1 is x0 minus I know Jacobian of x0 inverse times f of x0. This is the formula. Now, this is x0. F of x is what we wanted to like be 0, but is not right now. So we go to the second guess. Second guess, based on that formula, based on this formula, we find what should be our second guess. Okay, based on Newton-Raphson rule, this should be closer to our accurate solution. So we find that this is the second guess. We put that into the evaluation and see if it's satisfied the condition or not.
Do you use that same Jacobian inverse?
No. Then same function, different values. Because now it's j of x1 instead of x0. Same function. This is the Jacobian. Yeah, this is the Jacobian. For each guess, you put in the numbers.
So
Yeah.
that's
Yeah. Yeah, sure. So this is, and iteratively, you would go toward the point that now the f of that f you are that is condition of your acceptance of the solution when it's satisfied or is close to satisfaction, then you say, okay, we are good. This guess is close enough to our accurate value. We are going to use it as our answer. Are we good? Any question? No? Okay, if there is no question over there, and so perfect. That's very good. Then the session is over, and have a great rest of the day.